Hi everyone. With this video, we'll cover different versions of YOLO post the first version. This one is going to be in 3 parts, where in the first part, which is this video, we'll cover YOLO v2, getting into all the changes from YOLO v1 to v2. We'll also look at YOLO v3 and end with an understanding of the entire architecture of YOLO v3. In the next part, we'll deep dive into all the components of YOLO v4, like drop block, cross-stage partial connections, complete IOU loss, and so on. And just like the first part, at the end, understand the architecture of YOLO v4 in detail. Finally, in the third and last part, we'll cover YOLO v5. So let's begin this one with YOLO v2 or YOLO9000. And before getting into changes from previous version, let's do a very quick recap of YOLO v1, which was covered in the last video. Do take a look at that first if you aren't familiar with YOLO at all. In YOLO v1, we take the input image and divide it into S cross S grid cells. During training, each target ground truth object is assigned to only one of these S cross S grid cells. That is the grid cell which contains the center of the target object. For each of these grid cells, YOLO predicts B bounding boxes. The responsible box predictor during training for each cell is that box out of the B boxes predicted which has the highest IOU with the ground truth. And we train YOLO to modify the responsible box predictor to be as close to the target as possible. For each box prediction, YOLO predicts 4 localization parameters. The localization parameters are width and height, which is relative to the width and height of image, and X and Y parameter predictions, which are offsets from the top left corner of the grid cell of the box. For instance, let's say we are predicting this blue box, which is a prediction of the center grid cell. Then if this is the center of our predicted box, YOLO will predict these two offset values from the top left corner of this cell. Hence, during inference, we take the XY offset predictions made by YOLO and shift them by the grid cell corner locations to convert the box coordinates from grid cell space to image space. Apart from these 4 localization parameters, YOLO predicts a confidence or objectness score, which captures how likely the box contains an object and also how good a fit this box is for the underlying object. And we had seen in YOLO v1 video that during training, the objectness score target is the IOU between the predicted box and the ground truth box. Hence, for each box prediction, we end up having 5 parameters. And we have multiple box predictions per cell. Let's call that number B. In addition to these 5 B predictions per cell, YOLO also predicts C class conditional probabilities for the cell, indicating how likely that class is present in the cell. Note that these are one set of class probabilities for each cell rather than for each box, which gives us a total of 5B plus C values predicted for each of the S cross S grid cells. In our implementation, we trained YOLO v1 on VOC dataset, which has 20 classes, and for each cell, we predicted 2 boxes. Hence, we ended up with 30 values per cell. For training YOLO v1, we first pre-train our network, which was a CNN, on ImageNet classification task, and then it was fine-tuned for detection. During fine-tuning, the network takes an image as input and using additional detection-specific convolution layers and FC layers at the end, produces an output that can be reshaped to a S cross S grid with 5B plus C channels. These 5B plus C channels represent the prediction values for each of the S cross S grid cells. The channel values at the first cell location represent the prediction values by the model for this grid cell. And similarly, the channel values in the last one is for this image grid cell. With YOLO v1, we were able to perform detection at real-time speed. If you compare to the two-stage method of faster RCNN, where we had a detection speed of 7 fps, with YOLOv1, that increases to 45 fps. But this increase in detection speed unfortunately also leads to loss in detection accuracy. So there was a lot of room for improvement for one-stage detection as far as accuracy was concerned. The authors of SSD filled this gap with their model achieving similar performance, rather slightly higher performance than faster RCNN on VOC dataset, and all this while matching the speed of YOLOv1. For the rest of YOLO videos of this series, we'll see how different YOLO versions keep pushing the boundaries of faster and more accurate object detection. Which brings us to the first upgrade from YOLOv1 to V2. The main theme of YOLOv2 is to take YOLOv1 model and make it better, faster, and stronger. And we'll be going over the specific modifications that are done to achieve this. First, for making the model better. So these are groups of changes which are meant to improve the detection accuracy of YOLOv2 model, starting with batch norm being introduced in all the convolution layers, which was not there in the official implementation of YOLOv1. This simple change brings about more than 2% MAP improvement by improving the convergence of the model. Next is fine-tuning the classifier during the pre-training stage on higher resolution images. In YOLOv1, our backbone is first trained on ImageNet classification task, where usually the image inputs are 2:4 x 2:4. Then during detection fine-tuning, we subject the pre-trained layers of this model to inputs of 448 x 448, because a higher resolution input will allow us to extract finer details and be better at detecting small objects. But now during detection, the model has to adapt to this different resolution input while trying to learn how to detect objects. To ensure that the network gets adapted to this higher res input prior to detection fine-tuning, we take the network trained on 2:4 x 2:4 inputs of ImageNet and first fine-tune on ImageNet itself, but with 448 x 448 inputs for a few epochs. Then once the network has adapted to this new resolution, we do our detection fine-tuning as usual on 448 x 448 inputs. This now gives us mean average precision close to 70. Let's move to the third change. Our final prediction layer in YOLOv1 was an FC layer. We now make the entire YOLO model fully convolutional and also adopt the anchor box approach of faster RCNN for making box predictions. If you aren't aware about anchor boxes, I've covered that in my faster RCNN video in detail, so do take a look at it if you feel you need to review anchor boxes. Basically, for each grid cell, we now make box predictions as offsets from a set of predefined anchor boxes or prior boxes. So rather than predicting box parameters, we'll predict parameters that will transform these predefined anchor boxes to prediction boxes. This should simplify the problem, as rather than learning to predict boxes, the network now has to learn a simpler task of how to transform these existing boxes. To do this, we make a set of changes. We first take the YOLOv1 network and replace FC layers with convolution layers. The final prediction convolution layer will now be having 5B plus C output channels, since as of now all we have done is replace FC layer with convolution layers. But this number of channels will soon change. With an input of 448 x 448, our final conv layer output in YOLOv1 would be 7 x 7. We now remove a pooling layer to have the final output to be 14 x 14. This does two things for us. It allows us to predict more boxes, because for each grid cell we would be making predictions. So now rather than 7 times 7 49 grid cells, we have 196 grid cells. So this should allow us to get higher recall. Secondly, we are now working with higher resolution features than before, which should ideally improve our accuracy on small-sized objects because we have finer features to work with. We also changed the input of the network to now be 416 cross 416. This is primarily so that the final feature map will have odd number of grid cells along width and height. A common case of detection images is that a large object that needs to be detected is at the center. With odd number of grid cells, there would only be a single center cell, which allows us to have only one cell predicting such objects instead of 4 nearby cells, which would be the case if our final feature map has even number of grid cells along height and width. The last set of changes in this group is to introduce anchor boxes and perform all predictions for each of the anchor boxes. Remember, in YOLOv1, we were only predicting one set of conditional class probabilities for each cell. That means one cell can only possibly predict one kind of object. Now we are modifying that to have one set of class conditional probabilities for each anchor box or prior box. That means if there are 5 prior boxes for each grid cell, then we can possibly predict 5 types of object per cell, allowing us to be better at handling situations where the same grid cell ends up being responsible for predicting multiple types of object. This also changes our output shape. Assuming each grid cell now caters to B prior boxes, then instead of 5B plus C channels, with C being number of classes, our output shape is B times 5 plus C. C because we are making class predictions for each of the B anchors or prior boxes, and 5 because for each of those prior boxes, we are predicting 5 values. 4 of them are box offsets for X, Y, width and height, and the 5th is objectness score, same as YOLOv1. Do note that the C values are still class conditional probability, which means during inference we'll continue to multiply the objectness score with this class conditional probability to get actual class probabilities, same as we were doing in YOLOv1. The authors of YOLOv2 use a different mechanism of anchor boxes implementation than faster RCNN. In faster RCNN, for anchor boxes in RPN, the authors went with 9 anchor boxes with specific scales and aspect ratio. But there was no specific reason why 9 anchor boxes were chosen, or why we decided to have these scales and aspect ratios. And these choices might not even be optimal for all datasets. Like, what if our dataset only has small sized objects? Then what's the point of having these large scale anchor boxes? In YOLOv2, we take a different approach. Rather than simply deciding to choose prior boxes that cover different possible scales and aspect ratios, we use k-means to pick them. Here's what we do. We first plot all the ground truth boxes in our dataset. So this graph has width along x-axis and height along y-axis. Let's plot the ground truth boxes in VOC dataset, normalizing them to have width between 0 and 1. 1 meaning the ground truth box has the same width or height as the image. Then we'll get this plot. To give better clarity, all these points would be large square boxes, as they have similar width and height, both being close to image dimension. These all would be boxes with large height but small width. These would be wide boxes of small height, and lastly these would be small square-like boxes. After you run k-means on these sets of boxes with k equals 5, you will end up with these cluster centers that are representative in terms of scale and aspect ratio of all the ground truth boxes present in our training dataset. For distance measure of k-means, the authors use 1 minus IOU as the metric, where IOU is the overlap between the box point and the cluster center. For VOC dataset, we get these cluster centers. Here we have simply taken the width and height using xy coordinates of the cluster center. In practice, we would do this for a bunch of k values, and for each of those compute average IOU between cluster centers after k-means and the ground truth boxes. So how do we compute average IOU for a given k? To do that, for each ground truth box, we pick the closest centroid and compute IOU between the ground truth box and the closest centroid. And after doing this for all the ground truth boxes, the mean of those IOU values that we get is the average IOU for that particular k. Then we decide the best k based on factors that are important for our detection system. A higher value of k means you do get a higher average IOU, but you also end up with a more complex model because you have more predictions per cell, more time for the network to learn to compute offsets from these k priors. NMS also becomes computationally more expensive, and so on. Whereas on the other hand, a small value of k means that your priors do not even effectively represent the diversity of boxes in the dataset. Based on these trade-offs, for VOC, the authors use value of k as 5. The reason we do this k means to pick these prior boxes is that these prior boxes are better starting points for the box predictions of our dataset. Hence, the network would find it easier to learn transformation from these sets of boxes. For VOC dataset, one of the most common objects is of class person, which could be a reason why, after running k-means, we end up with more tall and thin boxes. So makes sense to attribute more anchor boxes to capture that aspect ratio. Furthermore, there are extremely few ground truth boxes which are short and wide. So why bother having an anchor box catering to that aspect ratio? By using hand-picked anchors or prior boxes, as in faster RCNN, we wouldn't really have made use of these dataset properties in the design of anchor boxes, which the clustering approach of YOLOv2 allows us to do. So now our model will make box predictions by predicting offsets from these 5 prior boxes, centered on each of the S cross S grid cells. And during training, given a ground truth box, we find the grid cell assigned to that box. This part is same as YOLOv1. But now out of all the prior boxes, we pick the one that has highest IOU with the ground truth. That becomes the responsible box. And YOLOv2 is trained to generate transformation parameters that transform this responsible prior box to the target ground truth. There is one additional change as far as box predictions are concerned. In RCNN variants, we saw that the authors parameterize the transformation from anchor or prior box to ground truth box using 4 parameters: Tx, Ty, Tw, and Th. These were the exact definitions for the transformation parameters, where x, y, wh are center coordinates and width and height of ground truth, and xa, ya, wa, and ha are values corresponding to anchor box. If we follow the same box transformation parameterization, then given a predicted transformation value Tx and Ty, our predicted box center will be this. Now since Tx and Ty prediction is not bounded, then this anchor box can end up anywhere in the image after being transformed by the parameters predicted from the model. The authors of YOLOv2 find that this unconstrained formulation leads to instability, where with random initialization, the model takes a longer time to produce meaningful outputs. To fix that, the authors use the same mechanism of XY prediction as YOLOv1 with a minor change. Like YOLOv1, for XY predictions, given the center of ground truth box, the model is trained to predict offsets from the top left corner of the grid cell that contains the center. So for this green ground truth box, this is the center, and the green grid cell contains that, which means YOLOv2 learns to predict these offsets from the grid cell corner locations. This is same as YOLOv1. The minor change in YOLOv2 is presence of sigmoid activation to constrain the output from 0 to 1, which means our predicted xy coordinates will be these. Note that our width and height transformation are still same as faster RCNN, where WA, HA are width and height of anchors and W and H are those of ground truth box. So our predicted width and height will be this WA times E raised to the power TW and HA times E raised to the power TH. The key difference from faster RCNN is that now our approach for handling XY coordinate predictions and WH predictions are distinct. The network is going to learn to predict width and height by learning to predict correct transformation parameters for transforming prior boxes to ground truth boxes. But this will only be for width and height. For X and Y, the network will be learning to predict offsets of center from grid cell location. So both grid cell location and prior box width and height take part in modeling our predicted box location. This sigmoid activation is actually also used for objectness prediction to bound that also from 0 to 1. These entire set of changes, right from using prior boxes, k-means, and logistic activation, bumps our MAP to 74.4. But this number also includes an update to network architecture, which we'll come to later. The next change is to make further improvements on localization accuracy for small objects. Up till now, we have one prediction layer catering to 5 anchor boxes for each of the grid cells in the last feature map, which was 13 x 13. In the SSD video, we saw how the authors, for smaller objects, use earlier layers feature map to get fine-grained features at higher resolution. So if we had to do the same for YOLOv2, we would use this 26 x 26 feature map and attach a prediction convolution layer on top of it as well to get localization, objectness, and classification scores for all anchor boxes for all grid cells in this feature map. And these prior boxes would be of smaller scale. But for YOLOv2, the authors take a different approach. They add a pass-through layer that brings in features from this 26 x 26 resolution feature map. In the pass-through layer, this is what happens. Let's assume C2 to be channels of the 26 x 26 feature map and C1 to be the channels of 13 x 13. We rearrange to move from C2 x 26 x 26 to 4C2 x 13 x 13. Now that both the feature maps are of the same spatial size, we concatenate them together and the prediction layer now operates on this concatenated feature map, which has lower as well as higher res features to make better predictions for small scale objects. To make sure we understand what's exactly happening behind this pass-through layer, assume this C x 4 x 4 is our higher res feature map. We'll see how this will be rearranged to get 4C x 2 x 2 feature map. This exact operation will be used to convert from 26 x 26 to 13 x 13 or any C x M x N to 4C x M by 2 x N by 2. We combine chunks of 2 x 2 grid cells into one spatial block. Because our feature map was 4 x 4, we'll end up with these 4 spatial blocks. If our feature map was 6 x 6, then we would have 9 spatial blocks. And when the feature map is 26 x 26, then we would have 169 such spatial blocks. Each of these blocks will be of shape C x 2 x 2. The rearrange happens such that each spatial block is reshaped to 4C x 1 x 1. So basically move everything along the channel dimension for each of the spatial blocks. The final output is same as what we would get by combining these 4C x 1 x 1 grid cells spatially, with the final shape being 4C x 2 x 2. Here we get 2 x 2 because we had 2 times 2 4 spatial blocks. In the generic case of input feature map being M x N with C channels, we would have M by 2 times N by 2 such spatial blocks, and the output would become 4C cross m by 2 cross n by 2. So this is how the 26 cross 26 feature map gets converted to 13 cross 13 and then gets concatenated channel wise with the existing 13 cross 13 feature map. Using this combined high resolution and low resolution features for prediction, we further get a 1% increase in MAP. The last part to make YOLOv2 better is multi-scale training. This change focuses on adapting the network to inputs of different sizes. Unlike YOLOv1, where during detection fine-tuning, all input images in dataset were resized to 448 cross 448, we now feed the network images of different sizes throughout the course of training. Every 10 batches, YOLOv2 picks a new image dimension size from a pool of sizes and resizes all input images fed to the model during training to this new image dimension. This way, we end up with a model that can detect objects from various input image sizes. So during inference, we get to decide what size we'll be feeding to the network, depending on our desired trade-off between speed and accuracy. Feeding a low resolution input will allow us to work with higher FPS, but will also result in less accurate detections. Whereas on the other end, large resolution input will increase accuracy but also lower detection speed. With multi-scale training, we now end up with an MAP above 76, as our detector is more robust to objects of different sizes. Now we move on to the change that authors make in the network architecture to make it faster. Essentially, this is just switching to darknet 19 as the base network. In YOLOv1, we had a base network architecture which was GoogleNet with few modifications that we went over in the previous video. Most of the detection systems like faster RCNN use VGG16 as the backbone for their detection model. If we compare VGG to YOLOv1 backbone, YOLOv1 backbone had much fewer operations, leading to a faster detection system. But when comparing the classification accuracy during pre-training stage, it was also less accurate. The authors of YOLOv2 propose a new classification model, darknet 19, which is more accurate, even more accurate than VGG16, while having lesser computations than even YOLOv1 model. This makes darknet 19 a much better backbone for a faster and more accurate detector. The main aspect of this architecture is presence of 1x1 convolutions to reduce the channel dimension prior to 3x3 convolution layers, and batch norm for all convolution layers. Similar to YOLOv1, for fine-tuning this network for detection, the authors remove the last convolution layer and add additional convolution layers for detection. During detection, we work with 416 cross 416 images, so these output shapes will change. And these are the 4 convolutional layers added during detection fine-tuning. The prediction is done via a final 1x1 convolution layer predicting values for all grid cells. The final convolution layer will have B times 5 plus C channels, where B is the number of anchor or prior boxes and C is number of classes. For VOC dataset with 5 prior boxes and C being 20, our final prediction 1x1 convolution layer will have 125 channels. Just like we saw before, we also have a pass-through layer to convert 26x26 features to 13x13. The authors also add a 1x1 convolution layer before that. This reduces the channels significantly prior to the pass-through layer, which is going to return a 4C channel output for a C channel input. The pass-through layer output is then concatenated with the output of third last convolution layer. And now the second last conv layer, rather than working on the output of previous layer, works on this concatenated feature. Now we are at the last section, which is making the model stronger. Most of the detection datasets cater to a relatively small number of object categories. So the scale of our detector, in terms of number of categories that it can detect, will always be limited. The authors of YOLOv2 identified an approach that allowed them to go beyond this dataset limitation. Specifically using joint training for classification and detection, with YOLOv2 we are able to detect more than 9,000 categories. So one of the main reasons of small detection dataset sizes is that detection annotation is costly. Classification annotation, on the other hand, is relatively cheaper, which is also why we have huge number of images covering wide variety of classes. The main idea here is to use this large available classification data to strengthen our object detector. So as an example, let's use Coco detection dataset, which has these small number of categories. And these are all the classes present in ImageNet 21K classification dataset. Obviously, there is a huge difference in the number of classes in both datasets, but let's see how we can use this to our advantage. The authors use WordNet, which is a language database that structures how different concepts relate to each other, and also groups words into sets of synonyms called synsets. Using WordNet, the authors build a hierarchical tree of concepts that allows them to merge categories of Coco detection dataset and ImageNet classification dataset. Here you can see that we have coarser detection categories as well as finer classification categories merged together. Our model will predict classification scores for all the concepts or nodes in this hierarchical tree. Now usually for classification, we have a softmax to convert the logits predicted for each class into probability scores. But here the classes are not mutually exclusive. For example, cat and dog, which are nodes having the same parent, are indeed exclusive, but cat and animal are not. To handle this, the authors compute softmax only for all nodes that are specific kinds of the same general concept. So according to this tree, animal, artifact, natural object and phenomenon are all specific kinds of physical object. So we'll have one softmax over these. Similarly, cat, dog, fish are all kinds of animal. So we have another softmax covering these groups of classes. And then further down the tree, we have two kinds of cat. So another softmax for them. And like this, we'll cover the entire tree. Including all the concepts in the final tree used by the authors, YOLOv2 caters to close to 9,000 categories, hence the name YOLO9000. So now how do we train this using data from both classification and detection datasets? So when our model during training gets a detection image, we repeat the same set of steps. Get the responsible grid cell anchors, compute the predicted and target transformation parameters for the box, and then we compute localization and objectness loss. For classification loss, however, we proceed differently. We get the path from ground truth class up to the root node, going from child to parent node one after another till we get to the root node. So here our class label is cat. So we'll go from cat node all the way to root node. For detection images, we'll only backpropagate classification loss at or above the corresponding level of the label. And we train the model to give higher probability for all the nodes that are present on that path. In this case, our first level is cat, dog and fish. So we train the model to give the highest probability for the cat class amongst these three classes. And remember, logits for these three classes were all covered under one softmax. For the next level, we train the model to give highest probability for animal class amongst all these classes. So what this will do is that after training at test time, when the model sees an image that has features very similar to what it understands as animal But the model isn't really sure which animal it is, maybe because its category is not present in the detection dataset. But even then, the model could predict a label of animal for that object with high confidence, while being unsure whether it's cat, dog, or something else. So this was for a detection training data point. But what happens when we get a classification dataset image? Now the model will not backpropagate localization loss at all. For classification loss, we first find the bounding box that has highest prediction probability for the ground truth class. This means we check the prediction probability for the ground truth class for all box predictions at all cells. For this image, assume that when we find that predicted box, we get this red colored box. Then the classification loss is only computed for the class predictions made by this selected box. For this box's class prediction, we train the network to give highest probability to all the nodes along the path from the ground truth class all the way up till the root node. So basically, in addition to all the class groups that we saw in the previous example, we also cover this group which has two kinds of cats. The authors also assume that this selected box should overlap with the ground truth by at least 0.3. So if the current objectness prediction of this predicted box is less than 0.3, we'll compute objectness loss assuming a target of 0.3. But if the current objectness prediction is already greater than 0.3, then we'll ignore it and not backpropagate objectness loss as well. So that's for training when we get a classification image. Now during the classification loss computation, I said that we'll select the box that has highest prediction probability for the ground truth class. But for each predicted box, we would have this tree of classification scores covering 9,000 categories. So how do we find the probability score for the ground truth class for this box? To do that, we keep on multiplying conditional probability scores for all the nodes on the path from the root node to this ground truth class node. So we start with the root node's probability. And for this, the authors just use the objectness score predicted by the YOLOv2 model for that box. Now say the objectness prediction ends up being 0.99. Then we go down the path and multiply this with the conditional probability of animal class. This will be animal class index probability after softmax on this group of classes. We then multiply with cat class prediction, which will be cat class index probability after softmax on the cat dog fish group. And finally multiply with the ground truth class probability using the last group. This product will give us the probability of Persian cat for this box. This is exactly how, at inference, we predict the desired class and score. We keep going down from root node and at every level choose the class with the highest score, and then go further down that path till either we reach a leaf node or a level where our highest classification score does not meet a predefined threshold. Let's say the conditional probability for Persian cat predicted by our model was 0.5 and our predefined threshold is 0.75. So that means during inference, as we are coming down from root node, we'll stop at cat class itself and not go down any further. And the predicted label for this box will end up being cat, because that's the last level where we met our threshold of 0.75. So that's all the changes from YOLOv1 that authors mention in the paper. There is no mention of loss in the paper, so the best we can do is take a look at the darknet YOLOv2 code and using the gradient mentioned for different components, make a guess for the loss used. For doing this, I've used YOLOv4 repo, which is forked from official YOLOv2 repo itself. The reason for choosing this is because in this we have YOLOv2, v3 and v4 code as well, and the authors have responded to numerous questions to make sure people understand what's happening in the code. So let's get into YOLOv2 Loss. Each ground truth target is now assigned to a pair of grid cell and prior box, where grid cell is the cell that contains center of the target, and prior box is that prior for the grid cell which has the highest IOU with the target. This will be our responsible predictor box. Now we are left with two types of boxes: predictor boxes that have IOU less than a threshold with all ground truth boxes, and predictor boxes that have IOU greater than threshold with any ground truth box. For the first, where IOU is less than threshold, objectness loss is MSE between 0 and objectness prediction with sigmoid activation. I have put a snapshot of the code where gradients are computed. So if you're really interested, you can take a look around the code as well. The deltas in the code snapshot that I have provided represent the gradients. Predicted boxes that have IOU greater than threshold with some ground truth box but aren't the responsible predictor, for them the objectness loss is ignored. For responsible predictor boxes or foreground boxes, objectness loss is MSE between IOU of responsible predictor box with ground truth and objectness prediction with sigmoid activation. This rescore here will be 1 for YOLOv2. Classification loss is just cross entropy with softmax activation. Localization loss for Tx and Ty is MSE between Tx and Ty and prediction of Tx and Ty with sigmoid activation. Localization loss for Tw and Th is MSE between target and predicted Tw and Th. In implementation, the authors also use an additional loss for the first 12k steps, where they compute localization loss between transformation targets for prior boxes and predicted transformation parameters. So it's like you're learning to predict the anchor boxes itself, which is why your Tx and Ty target will just be 0.5. But this is only done for non-responsible prior boxes. For the responsible ones, you'll obviously learn the transformation from the assigned ground truth. There's nowhere a mention of this in the paper, so I'm not really sure why do this or what benefit this gives. One guess that I can come up with is probably this was implemented when they were having stability issues, and it was meant to ensure that the network quickly learns to predict slightly meaningful outputs by predicting the anchor boxes itself for all cells, and from there on learn to predict better modifications of these anchors. I don't know if this ends up giving significant help, if any, especially after we have bounded activations for box predictions. But this prior loss term is anyways not used in future versions. So that's it for the losses. Once we train YOLOv2 with these set of changes, it ends up being a very fast detector, while being as accurate as SSD 500 model. And because of multi-scale training, we have a whole lot of input sizes to choose from to have a detector which matches our accuracy and speed requirement. Now let's move to YOLOv3. YOLOv3 was just a small set of incremental improvements over V2, with the most important change being the move from darknet 19 to darknet 53. And rather than doing predictions just at the final feature map, we do predictions at 3 different scales. So this was our darknet 19 and this is darknet 53. Apart from the obvious change of increased number of layers, we can see that the authors added residual connections in the network. And instead of max pooling, we now have strided convolutions to allow the network to learn how to reduce the spatial size in a manner that is best suited for the task. Let's go through this entire architecture because it will help better understand the multi-scale prediction layers. Plus, this will also have a lot of similarities with YOLOv4, which we'll look at in the next video. We start with a 3x3 convolution layer, and we'll keep track of the spatial size as we move through the layers through this size field. Then we have a downsampling convolution. Post that, we have our first residual block, which is 1x1 convolution layer to reduce channels, followed by 3x3 convolution layer, and a residual connection. This entire residual block will be repeated n times, where n will have different values for different stages of network. For the first block, n equals 1. And this residual block will operate at spatial dimension of size by 2. Then we have another downsampling layer, and now we'll simply repeat this residual block plus downsampling layer with different values of n. For the next stage of network, we have n equals 2, and the spatial dimension of feature map is size by 4. Then we have n equals 8, working at size by 8 spatial dimension. The second last stage has again n equals 8 residual blocks, with dimension being size by 16. And finally we have 4 residual blocks operating at size by 32, making the effective downsampling factor of the network to be 32. Post that, we have the classification layers. So all these layers end up being our darknet 53 backbone, which after pre-training on ImageNet classification task acts as a base feature extractor for YOLOv3. Just like YOLOv2, the authors take this network and add a bunch of convolution layers during detection fine-tuning stage. Specifically 5 convolution layers with kernel sizes of 1 and 3 are added. This is the detection feature output, to which we add a 3x3 convolution layer and a 1x1 convolution to make predictions. YOLOv3 makes predictions across 3 scales, and these are just the predictions using the lowest resolution features. So these will cater to the largest size boxes. In order to make predictions at other scales, the authors use FPN-like top-down pathway to aggregate low resolution but semantically strong features with finer high resolution but semantically weak features. Like FPN, we'll upsample the coarser feature map and combine with the higher res feature map. The exact implementation of these connections are a bit different than FPN, but the idea is same. The higher resolution feature map will have activations with more accurate localization, and the goal is to merge that with semantically strong features to get predictions at different scales. Let's look at how in YOLOv3 we make predictions at other scales. We take the detection feature output, the feature prior to these prediction convolution layers, and after a 1x1 convolution, upsample it to get feature output of size by 16. We concat this with size by 16 feature map output from an earlier stage of the network. To this, we again add 5 convolution layers, followed by a 3x3 and 1x1 to make predictions for prior boxes of a smaller scale. Because of more accurate localization features coming from earlier stages of the network, this will give us more accurate predictions for smaller boxes than if we attempted to get small anchor box predictions from this higher level feature itself, like we did in YOLOv2. This entire step of taking the feature just before prediction layers and adding convolution and upsampling is again repeated. And this time, we concat with size by 8 feature map output from an even earlier stage of network. Lastly, we do the same 5 convolution layers followed by 3x3 and 1x1 to make prediction for boxes of smallest scale. In YOLOv2, we had used 5 prior boxes and used k-means clustering. YOLOv3 also uses clustering to determine prior boxes, but they use k equals 9. The authors divide these 9 boxes across 3 different scales. On COCO dataset, the lowest resolution feature map caters to the largest scale prior boxes, having these specific dimension. The second prediction layer caters to these prior boxes. And the highest resolution feature map, which has finer features, caters to the smallest boxes of these dimension. The formulation for channels in the final prediction layer remains same as YOLOv2, that is number of prior boxes times 5 plus C, making it 255 for Coco dataset, where the number of classes is 80. And this will be the number of channels in all the 3 1x1 convolution layers that are going to act as our prediction layers. Apart from architecture changes, there were a couple of other specifications also that were made by the authors in the paper. Given a ground truth box, only one bounding box prior, the one which has maximum overlap with it, is treated as foreground. And those bounding box priors which have overlap greater than threshold but are not the best box are ignored. The specific value used for this threshold is 0.5. Remaining prediction boxes are treated as background, and they end up impacting only objectness loss. The objectness target during training is now either 0 or 1. For classification, the authors, unlike typical classification systems, model the problem as multi-label classification, where rather than softmax, they now use sigmoid. This allows them to move to datasets where the class labels are not mutually exclusive and have overlap in between them, like woman class and person class. These were the only major changes from YOLOv2 to YOLOv3. So with these, let's see how YOLOv3 fares in comparison to previous version. For comparison, up till now, we have been using performance on BOC dataset as the criteria. But from now on, we'll use Coco dataset performance as the comparison metric. This is because most of the future works have evaluated their respective models' performance on that itself. For Coco dataset, we use the AP metric, which captures average precision at a range of IOU threshold values. AP50 here captures average precision metric at 0.5 IOU threshold. I've covered AP metric in detail in one of my earlier videos, so do take a look at it if you are not familiar with it. On Coco, YOLOv2 got an average precision of 21.6. With YOLOv3, we now end up getting an average precision of 33. This jump is primarily because of a better backbone and prediction at multiple scales, leading to significant improvements in accuracy for small and medium scale objects. Though this variant ends up taking more time than YOLOv2, because note that this is not FPS, it's time taken for inference. So lower is actually faster. But with feeding the network with smaller sized inputs, we can achieve better object detection accuracy than YOLOv2, while being faster than that. Comparing YOLOv3 to other detectors on the AP50 metric, YOLOv3 ends up being the best in terms of speed, and its accuracy is also on par with the best performing models. But it's still behind if we use the AP at all thresholds metric. However, with future versions of YOLO, we end up even bridging that gap. So that was all about YOLOv3. This video was mainly to give an overview of changes made in YOLOv2 and YOLOv3. In the second part of this video, we will cover everything about YOLOv4, before finally getting into YOLOv5 in the third part. I should be able to publish the YOLOv4 video in a week or two, so see you then. Thank you so much for watching this one and have a great day.